Hello, students. We're going to take notes today on solving exponential and logarithmic equations. We only have a single day, and my plan is to show you the simpler examples in the video, and then when we get to class next time, we will go through some of the more complicated examples. So go ahead and title your notes and figure out the notes number and the date, and we'll be ready to go. Don't bother to take notes on the content on this first slide. So we're going to be solving equations, so I just want to remind you that the key to solving equations is always inverse operations. The key to solving equations, inverse operations. They undo one another. So for example, if you had to solve the equation x plus 6 equals 38, you would do the inverse of adding 6, which is subtracting 6. That would undo the adding of 6, and you would just get 32. Or if you had to solve the equation 6x equals 38, you would do the inverse of multiplying by 6, which is dividing by 6. That would undo the multiplying by 6, and you would have whatever 38 over 6 is. So inverse operations are key to solving equations. So the key to solving exponential equations, well, what's the inverse of exponents? It is logarithms. So logarithms are the key to solving exponential equations. So here's an example. Solve for x. 6 to the x equals 38. What we can do to undo the exponential part, 6 to the x, is use a logarithm. And since the base is 6, we can use log base 6 of the left and log base 6 of the right, the log of both sides. Technically, you could use log base 10, log base e, log base 99, log base whatever you want and still solve the equation, but I think the most logical choice would be log base 6. Now that we have this, think about the power property, which tells you that you can bring this exponent down to the front. And if you do that, you have x times log base 6 of 6 equals log base 6 of 38. And what is log base 6 of 6? Ask yourself, 6 to what power gives me 6? Of course, that's 1. So this quantity right here is just 1. X times 1 is just x. So x equals log base 6 of 38. That is the exact answer to the problem. We're going to answer with exact answers as well as approximate answers. But my emphasis is really on exact answers, especially when you have to use them for something else. Exact answers are going to preserve accuracy. Now it's possible that if you use a different log, you'll get a different looking exact answer that's equivalent to this. And what we want to do next is see how we would type this into the calculator. I think we've already looked at using log base buttons on our calculator. So if your calculator is able to do log base 6, that's great. Just type it in and you get the approximate answer of 2.03 if you round to the nearest hundredth. Now if your calculator is not able to do log base 6, there is something equivalent. You can change the base and make it log base 10 of 38 over log base 10 of 6. So this is using what we call the change of base formula. The 38 comes from the argument of the logarithm, and the 6 comes from the base of the logarithm. You're going to find that these give you equivalent answers. And in a similar way, instead of log base 10, we could use natural log. Natural log of 38 over natural log of 6 will give you the same equivalent answer. Again, the 38 just comes from the argument of our answer, and the 6 comes from the base of our answer. So all of these are equivalent and they are all acceptable. Log base 6 of 38 could be your answer, or this expression over here, or this expression over here. Okay, kind of made that slide look like a mess. Let's move on to problem number 2. solve for t. And again, we're going to give the exact answer as well as the approximate answer. We have e to the 2t equals 19. Okay, so what logarithm will undo e to a power? It would be log base e. And log base e is known as natural log. So natural log of the left and natural log of the right. And just like we saw in problem number 1, we could now bring this 2t out to the front. So we have 2t, that's using the power property, times natural log of e equals natural log of 19. What's natural log of e? Well, that means e to what power is e? And that is just 1. So this is just a special form of 1. So all we have is 2t times 1, so 2t equals natural log of 19. And finally, to get t by itself, divide both sides by 2. So our answer is natural log of 19 over 2. That's our exact answer. Chances are everybody would use natural log and not a different base for this problem. So we probably have the same looking exact answer. Put this in the calculator to get the approximate answer, and if you round it to the nearest hundredth, you'll have about 1.47. All right, let's look at problem number 3. Now, here's a key piece of information. If you look back at problem number 2, we had a base to a power equals a number, and we took the log of both sides. If you look back at problem number 1, we had a base to a power, and that equaled a number, and we took the log of both sides. So anytime you want to take the log of both sides, you need the form a base to a power equals something, some number. Once it's in that form with all the extra fluff taken away in the equation, then you're ready for logarithms. So when you look at problem 3, you'll notice there is a base to a power, but right now it's not by itself on that side of the equation. There's other extra stuff also there, like the -1 and the multiply by 18. So we need to clear out that extra fluff and stuff and get the base to the power by itself, and then we can take the log of both sides. So I'm going to add 1 to both sides of the equation, and then divide by 18. And we could simplify 10 over 18. That would be 5/9. Now look what we have. We have a base to a power equals a number. We are ready to take the log of both sides. So what kind of log do we want to use? The same base that we see in the problem right now. So we see base 1.04. So we can do log base 1.04, as weird as that is, of 1.04 to the x equals log base 1.04 of 5/9. Sometimes I write in the parentheses around the argument. Sometimes I don't. It doesn't really have to be there most of the time. Okay, as we saw in problem 1 and problem 2, what's going to happen over here on the left is we're going to bring the x down to the front. We will have x times 1. So our exact answer is x equals log base 1.04 of 5/9. And then to put that in the calculator to get your approximate answer, if you can, just do log base 1.04. But if your calculator won't do that, again, use the change of base formula, and you can change it to log base 10 of 5/9 over log base 10 of 1.04. This could go in the calculator. You'll get the same answer. Or instead, you could change it to natural log of 5/9 over natural log of 1.04. Either way, you'll get the same answer you would get using log base 1.04, and that would be negative 14.99. Once again, I am most concerned with the exact answer, but the approximate answer is often used, especially in word problems, so we should be accustomed to finding it as well and making sure we can use our calculators with accuracy. Next, we're going to switch gears and solve some logarithmic equations. The key to solving logarithmic equations, again, this goes back to inverses. So the key to solving all equations is inverse operations. The key to solving exponential equations was logarithms. So the key to solving logarithmic equations would be exponents, the inverse of logarithms. And let's see if I can spell exponents. There we go. Again, we're giving the exact answer as well as the approximate answer. And problem number 4 is solve for t, log base 5 of t equals 7. Okay, so what I want to do is something that will undo a logarithm, and exponents will undo a logarithm. And the process I'm going to use is called exponentiating. Kind of a fun word. Exponentiating is where each side of your equation becomes the power on something. So notice we have base 5. So each side of my equation will be the power on 5. 5 to the left side of the equation equals 5 to the right side of the equation. 5 to the left equals 5 to the right. We did the same thing to both sides, so we kept everything equivalent. What is 5 to the log base 5 of t? Notice the inverse operations there. Log base 5 and 5 to a power cancel, leaving you with t. So t equals 5 to the 7th. And then if you put that in your calculator, 5 to the 7th is 78,185, or excuse me, 125, 78,125. And that's our exact answer. There's really no approximate answer this time, so only give approximate answer when it makes sense. Okay, let's take a look at number 5. Okay. So just like we saw with the exponential equations, there's a particular form that your logarithmic equation must be in before you can exponentiate. So if we look back at problem number 4, you'll notice that I had a log of something equals a number. No other extra fluff and stuff, just a log of something equals a number. So if you want to exponentiate, you need to have just the log of something equals a number. I feel like I'm missing a shape there. Let's see, let's go back. What did I do? Oh, the log of something equals a number. Okay, so just to be consistent here, we have the log of something, whatever the something is, equals a number. Once you get it in that form without any extra stuff, then you can exponentiate. So let's take a look at number 5. We have 3 times log of x equals 11. So we do have the log of something equals a number, but there's also that 3 on the outside. So I need to get rid of that before I can exponentiate. So we're going to divide both sides by 3. Now we have just the log of something equals a number. Now we are ready to exponentiate. So some base to the left equals some base to the right. What base do we want to use? Look at our logarithm. It just says log. So that means it's a common log, which is base 10. So we want to use 10. 10 to the left equals 10 to the right. 10 to the log base 10. These are inverse functions that cancel, leaving us just with x. So x equals 10 to the 11/3. That's our exact answer. And if we plug that in the calculator, we will get something like 4,641.59 as the approximate answer. All right, let's do one more logarithmic equation. Solve for x. Remember, if you want to exponentiate, you need the log of something equals a number. That's exactly what we have. So we are ready to exponentiate. And the base of our logarithm is 2. So we're going to do 2 raised to the left equals 2 raised to the right. And on the left, the 2 to the power and the log base 2 are inverse functions which will cancel, leaving us just with 3x plus 2. And on the right, 2 to the 5th is 32. So let's just keep going until we get x by itself. Subtract 2 from both sides and divide by 3. X equals 10 is our exact answer, and there's no need for an approximate answer here. So again, we have our basic examples, kind of our easy to medium examples in this video, and then in class time we'll do a little bit of practice with the medium level and we'll move on to the more challenging examples, and then you'll have a lot of class time to do some practice. Thanks, guys.